The same one where we stopped.
Can you hear me?
Can you hear me, Arjun? Seems I think neither pathway nor.
Oh, okay.
I,
So Srikar,
sorry.
you can hear me.
I can hear you now.
Oh,
Can you
you guys
hear?
can hear me now?
I can hear you now. I had muted by mistake. I think it's
Oh,
because
okay.
maybe.
No problem. I think I have the question, whatever I wanted to ask at that time is clear now, so it's okay. At this point, I don't have the question. I think at that time, I wanted to ask whether when you are saying there exists, whether it's up to that equivalence or not, but it's clear. It's up to that equivalence.
Yes, yes.
Yeah, that's clear. You immediately made it clear, so it's okay. Thank you, Srikar.
Okay, so if you recall, I had said that T0nx is supposed to be n times mu of x plus n to the c times some z. This z was my Tracy-Widom distribution. So in d equals 2. And this again in d equals 2 was 1/3. So this is a conjecture. So here's what is known and conjectured about C. So in one dimension, it's 1/2. Why is it 1/2? This is simply the central limit theorem. Okay? So T0 and x is just the sum of IID weights, T equals 1 through nx or tau I. And so this we know is n times expectation of tau I plus n to the 1/2 z, and here z is known. In 2, it's supposed to be 1/3, so it gets smaller. And this is only known in last passage percolation with exponential weights. And 3, so on, unknown. But as d gets very large, we know it gets very small. And so this is known, I think. We know that it's good. So these two exponents, chi and xi, are related. So in 85, Hughes and Fisher said in d equals 2, you have the first KPZ relationship, that is 2xi minus 1 equals xi, and all d bigger than or equal to 2, and 2 chi equals xi holds only in d equals 2. So if you solve these two things in d equals 2, you'll get chi equals 1/3 and xi equals 2/3. So in the case of the simple random walk in 2 dimensions, if you go from 0 to nx, then you expect fluctuations of the order of square root n. So the intuition is that to find the maximal path, you have to fluctuate a bit more. And so that's why you see an exponent of size 2/3. And maximal or minimal path, the optimal path. Of course, none of this is known. These are all physics conjectures. However, I should say that this particular relationship has been explored quite well, starting with Newman. Under strong assumptions on their existence and the limit shape and so on, that we don't know. And in fact, I think the state of the art is Chatterjee, and he wrote a paper, I don't know when, maybe early 2010s, something like that, and that this was in the Annals of Math, in fact. But they are not foolproofs because they assume lots of unknowns, lots of strong assumptions about the limit shape. Okay, so that's the KPZ connection. I should also say these have been proved in the solvable LPP. Solvable LPP, or last passage population, and related models like Poissonian last passage, and so on. So we go back to 2001 and do Johansson. Okay, so again, more questions, and I'm asking questions because I somehow want to motivate you to join this field. In general D, give good definitions of C and give good definitions of C and chi. Show 2C minus 1 equals psi without assuming anything about mu and anything else. And 3, even show C strictly less than 1 without assuming anything again. So decreasing order of difficulty, but still open.
So why is the first one such a non-trivial point? I mean, you have a straight geodesic and you want to look at laterally from that. Is that not what chi should be?
I should say so chi is fair, fluctuations exponent. Show there exists such a number, for example. Show there exists such a number. Would be a better question. In C, for C, there are many competing definitions, so even that's a problem. And various inequalities can be proved, and so on. So, and it's not clear what's the right definition so that this can be proved. Chatterjee gave one such way under assumptions about the limit shape. Okay, so now I want to move on to, so for example, I can give you a flavor of the kind of theorem that you can prove under curvature. So I'll state this because it's a classical famous result. So theorem due to Newman and Pisa in the 90s says if F0 less than PC and expectation e to the alpha tau e is less than infinity for some alpha bigger than 0, and says if x is a direction of curvature for mu, then c less than or equal to 3/4 and chi bigger than or equal to 1/8.
Sorry, what do you mean by direction of curvature?
I'll go back to this picture I drew.
Yeah.
So here theta would be a direction of curvature.
Because of that estimate, or?
Yeah, because of this estimate. You assume this estimate holds, you have no idea that it does, but assuming it holds, you can prove this Newman-Pisa theorem. So for example, you could have, something nice and curved here, but as it gets down here, it could be flat and so on. We don't know these things, whether they happen or not. So what I care about, what I have been caring about recently, are infinite geodesic rays. So here we talked about, yeah.
So, one of the things which makes this a little more complicated is, I guess, the fact that we are, in some sense, we are in ZD, which is a discrete model, which is very difficult to rotate or reflect. So these are some of the things which make this analysis linked. Are there similar models in RD which are more tractable, or is it
Yeah, so Nishant asks, are there more tractable models with better symmetry? Because ZD is messy situation. The answer is yes. It's been explored quite well by Howard and Newman. You can have rotationally symmetric situations where the limit shape is a circle. So in RD with good symmetry, mu is a circle, and this is due to Howard and Newman.
This is, for example, that Poissonian LTP?
Yes, like that. Okay, so I'd mentioned these infinite geodesic rays. I can think of just indexing them by or describing them by the sequence of edges they take, or I could think of them as something like x equals x0, x1 in terms of their vertices. They're equivalent, only that they're infinite. And this is called a ray.
So, this Newman-Pisa theorem is for R2, is for Z2, or
Yes, this is in D equals 2. Not sure, I think it's in ZD. Let me check.
because you said chi goes to 0 as D goes to infinity, right? Because this theorem had a lower bound.
Yes, so this must be in D equals 2. And I'm pretty sure it's D equals 2. Newman-Pisa is in D equals 2. So the first question is, do infinite rays exist? Do geodesic rays exist? The answer is yes. So here's the argument. consider geo 0 say to nx for some fixed x, or n equals 1 to infinity. If we have continuous distribution, this is just some sequence of paths. Say this is the first path, that's 0 to ne1. Maybe I have another path going to say not ne1, this is just e1, that's 2e1, and that's 3e1, and so on. X is equal to e1.
Sorry, just an additional question.
Hmm?
GeoX is the set of all infinite geodesics.
No, geox is a geodesic that starts at x. A geodesic that starts at x. Goes off in some arbitrary
We have drawn
direction.
this like a tree, but it may not look like a tree. It can be quite arbitrary.
Which one?
The diagram that we do for geo.
Yeah, it's definitely a tree because you have unique geodesics. You can't have loops. But yeah. So Nishant asks, is this union a tree?
We can't have loops because we are in a continuous distribution.
We have
so
continuous
you would have a
distribution.
unique-
Unique geodesics.
Sorry.
Yeah, unique geodesics. So, what you do to construct gamma is to look at, you start at 0, and then you look at the 4 points, E1 minus E1, E2 minus E2. In general, you have 2D points, where D is the dimension. And then ask which one of these neighbors has infinitely many paths from this set in it. Maybe that's the neighbor E1, or maybe it's a neighbor minus E1. Okay, so I have some way of distinguishing between tiles, so I just pick, say, one of them minus E1. So one of its neighbors must have infinitely many paths going through it. Infinitely many paths from this set going through it. One of its forward neighbors, so to speak. There's no backtrack. Then maybe that's minus E1 plus E2, and so on. And so you keep constructing this path, and then it turns out that gamma is a geodesic.
There's just some compactness argument.
So this is, as Nishant says, compactness argument. Compactness in the sense that you're just descending down some subsequence.
Or diagonal line.
So the question is, we have at least one. So let me say. So questions.
I've shown at least one in every direction. Right? I mean, is that right?
I'm not
X,
sure
if you
because
fix X.
X is fixed, right?
there's no reason you can change.
It need not have a direction.
Yeah.
This gamma.
It need not have a direction. If you pick other y's and do this procedure, it might coalesce with gamma, and I want uniqueness up to finite. If they only differ on finitely many edges, they might be unique. So you can ask, are there more than one? So the answer is, due to Hoffman, he says yes.
Is this Chris Hoffman?
Yes, Chris Hoffman says at least 4. And in general, if sides B is the number of exposed points of B, then yes, that many. So what's an exposed point? For example, if I have a flat spot and I try to draw its tangent, then it will intersect the boundary of the shape in this whole interval. So that whole interval is non-exposed. The whole open interval is not exposed. But if you have some nice curved thing and you have a tangent line that intersects the boundary of the shape at only one point, then that's exposed.
So this is the argument saying that strict convexity of mu implies that infinity means geodesics.
Right. So as Nishant says, if you had a mu being strictly convex or the boundary of the shape being strictly convex, then you'll have infinitely many geodesics.
So just to clarify, for a circle there will be infinity.
Yes.
And for the diamond there will be 4.
Yes. At least 4. I don't know if it's exactly 4. So even in the L1 case, you can see that.
No, but you said if yes, that many.
At least.
Is it at least that
Where are there more? Sorry, I didn't.
many? You said if sides D is the number of exposed points of D, then yes, that many.
Yes.
Exactly that. Or
At least that many.
Okay.
You're right. And at least sides B.
This is probably a general B result, I'm guessing, that you can probably, like, I don't see why this should be feasible.
So a lot of these arguments, I'll show you one of these are trapping arguments. So they work well in D
I
equals
see.
to. They need curve theorem. So Nishant asks, is this restricted to D equals 2? And that was my answer. So to answer this question, he used a tool called Busemann functions, which Hoffman used a tool called Busemann functions. Main tool. And I'll talk about them in a second. They are very nice objects, very interesting objects. So an even simpler question is to ask, is sides B equal to infinity? That would be wonderful to ask for a large class of continuous distributions.
This is a reduced question, is it? I mean, you expect curvature everywhere in general?
Yeah, you expect curvature, you expect strict convexity. So they're always in descending order of difficulty. So I just want to sort of motivate where they come from. Okay. So one of my favorite theorems, set of theorems, state 2 now, are due to Newman. So they say the following, because they do not assume anything about the limit shape. They're general theorems. They just assume some moments for the weights, but I'm fine even for bounded weights as long as it's general enough. Because all of these KPZ things are supposed to be true in that case. It says for D bigger than or equal to 2. Oh, sorry, this one assumes something about the shape, but the next one won't. I'll show you what. Assume F0 less than PC and expectation e to the alpha tau e less than infinity for some alpha bigger than 0. Assume B is uniformly curved. Basically, by uniform curvature, I mean I go back to that relation I showed you and say that that constant does not depend on theta, on the direction. Theta implies uniformly curved, more or less. Then, almost surely, every geodesic has a direction. Every infinite geodesic has a direction. Has a direction. And two, for every theta, there exists a geodesic, infinite geodesic. Goes without saying. With direction theta. This is quite nice. Then it tells you something more. Theorem Busemann 96 says let D equals 2 and F continuous. Fix X in Z2. Then there exists D is a subset of 0 to 2 pi, a set of directions, such that the big measure of D is full 2 pi, and if theta in D, then probability there exists X, probability there exists geo1 of X and geo2 of X with distinct with direction of geo1 of X equal to direction of geo2 of X equals theta is equal to V. So this is going to be a very important theorem for us. So it's saying the probability that there exists a geodesic, I'll call it gamma 1, going in direction theta, and something disjoint at some point, also going in direction theta, cannot happen.
It is also saying something about fluctuations in this particular case. It's saying that the fluctuations can't be too much. Because if you were to fluctuate, then you would have two different geodesics.
It's you're saying it. Nishan's saying.
Of course, the geodesics are unique in this case.
If you have curvature, they're unique, but this doesn't assume anything about.
But if you assume that f is continuous, then also it is unique.
Finite geodesics are unique, but you could still have infinite. It's saying there are bad directions. There could be bad directions. We expect there to be no bad directions. So this theorem does not assume anything about shape. We like this. However, what's open is to show, for example, show the direction E1 is in D, or in this notation, show 0 in D. The angle 0 degrees is in B. That's all. Not more. Then we know more. For D equals 2 and theta in D, suppose geo1 of x, direction of geo1 of x equals direction of geo2 of x equals theta, then can you guess?
Geo1 x is equal to 0 to x.
Right. Geo1 of x equals geo2 of x. Sorry, you can't have this situation. I should say geo2 of y. Then geo1 of x equals geo2 of y. Meaning, if I have some geodesic in the direction x, in direction theta, and I have a geodesic in direction theta, then they must coalesce at some point. Must coalesce and stay together. And stay together. Why stay together? Because theta is in the good set B. Okay, so these are the two theorems that will inform our view of geodesics.
This is also given by Newman or by
This is due to Lecce and Newman. 96. So since these are in D equals 2, we can in fact show quite easily and show there exists a geodesic in direction theta in direction theta starting at every point x, from every x. Let me show you this argument. So there are at least, so you can show the probability that exists a geodesic in direction theta from one point x. With the Ergodic theorem, there must be a density of such points having a geodesic in direction theta. So there are at least two. So there's some geodesic starting at A, some geodesic starting at B, or any fixed x. This happens with probability 1 in fact. So what I will do is I'll just pick one of these geodesics, and I have to somehow trap it. We can assume we have some sort of directedness, but I'll form geodesics to points on A. So I'll form finite geodesics from x to, let's call that A. And I look at the union of these things, do compactness argument, obtain gamma of x, and this will give the picture where I have an A, I have an x, and I have a gamma of x that will be trapped in between. So this will be gamma of x, and direction of gamma of x will be equal to theta because it's trapped between the geodesics from A and B. It doesn't work in 3 dimensions. Very specific. Okay. So this is my picture, and I'll leave you with this picture. I have geodesics in direction theta, from every point on the lattice. So I have some sort of collection of infinite paths. Infinite paths, geodesics. Z and Z.
So, just asking,
Yeah.
like if we were actually doing this in 3 dimensions, and then I know that the positive density of points x have this geodesic in direction theta.
Yeah.
So couldn't I somehow form a cube around every x and somehow do a similar? Like there be so many points to which it is passing, so and I don't want this geodesic in between to escape. Okay.
There's a lot of room. So Nishant asked, can't you extend this argument to d equals 3? There's a lot of room in 3 dimensions. A lot of room in this room because it's in 3 dimensions.
I didn't get the argument. What is the argument? If there is, what did you show?
So I said I have at least 2 geodesics, one starting at A and one starting at B in direction theta, because theta is a good direction. Then I'm showing there's a geodesic from any x going in direction theta simply by trapping between A and B. I'm not shown some sophistication, but so you take the sequence of finite geodesics, do the compactness argument to get an infinite path, and show that it cannot that it's trapped between these two. And so because it's trapped between these two, it has direction. And so now we are in the situation where we have an infinite path from every point going in direction theta, and you can think for a second and say, okay, if I think of xz as a map from z plus to z2, meaning it's x sub z of k is its kth step, then instead it's equivalent to just think of xz of 1 minus xz of 0, sort of the vector field, this lattice vector field generated by these walks, and then you can reconstruct this these walks from this vector field.
So in 3 dimensions, wouldn't sort of the right analog be minimal surfaces
Yeah, I agree. I don't know too much about those. Nishant asks, wouldn't the right analog of this be in 3 dimensions, minimal surfaces? Yeah, possibly. There's lots of work that's been done in that direction. I'm not super familiar with that. Okay, so now I have a setting to study. I have my 2-dimensional lattice, and I have an arrow from every point, a random arrow from every point. And I'm going to study the flow of this vector field and ask, what's going to happen to the collective behavior of particles started from every point on the lattice?
Sorry, I missed. What are you doing now?
So I have a collection of geodesics that meet once they touch, going in direction theta. And now I'm saying, since there's one from every point, I might as well just look at the derivative of that vector, of these paths, the first step of these paths. That's an arrow in one of the d directions. And I can just simply give you arrows, say it encodes the same information as this collection of geodesic, and ask, how do these arrows behave? What's the collective behavior of these arrows? I will return to this question in the next class, talk about the connection to Busemann functions, and maybe state a couple of theorems. I'll stop here.
Any questions?
Despite your silly question, say in your IID, why can't I just translate this, like say finite geodesic between 2 points? Why can't I just translate it? I don't see why. You can just translate it. Will that also be a geodesic?
So
Why is it not?
So in the IID setting, you're asking, I have some weights here, say 3, 4, 2, 1, 1.5, so on. And suppose this path is the geodesic from say X to Y. Right? And so now you're saying, let's translate this guy to say this point and ask, is this a geodesic? Is that right? The weights are different.
Distribution is.
But I guess
This is a real life.
but even then, like if you use something like quantitative recurrence theorem, then you know to an extent maybe what he's saying is not so far.
Maybe. Could be. Like you'll encounter similar local situations
Situations, whatever.
with some density, yeah. Just the ergodic theorem is not.
I'm slightly confused about what assumptions you were talking under here.
Here, in this,
In this
Hmm.
argument, where you say the two geodesics are same, yeah, d equal to 2, that's bottom
yeah,
of the
this is
bottom.
these are the assumptions. Let d equals to f continuous, theta on the good side.
So under the curvature and all that.
No
Under that,
curvature, no curvature.
I mean, sorry, at the bottom where you prove this. Now the argument you gave that this one,
Hmm.
under what assumptions did you prove this? I was confused.
So there's a density of points on the lattice with a geodesic going in direction theta.
Okay.
That's guaranteed by the chain theorem. In that case, I'm claiming that from every point on the lattice you have a geodesic in direction theta. And that's it. Once one does that, you can reduce to arrows.
Any other questions? If there are
Any
questions
questions from
online,
online? Please
unmute
unmute and ask.
Okay.
So if not, we'll meet again on Wednesday, time 2 o'clock.